getting about time, so I'll just go ahead and introduce our next speaker. I guess welcome to day 2 of the summer school. I'm very excited to present Professor Barry Bradlyn, who will be giving 2 talks today. Professor Bradlyn was actually going to be here with us, but the airline gods had some other ideas, and so we are now going to be showing his presentations virtually. I think it will still go over pretty well, so we're very excited about that. So Professor Bradlyn, really the reason we're so excited to have him here is he's been a really important driver in the research of topological materials in the last 10 years or so. He did his PhD at Yale and then actually came here to Princeton at the Center for Theoretical Studies for his postdoc, where he did really seminal work on topological quantum chemistry. And then he joined the faculty of the University of Illinois in 2018, where he's continued to work in the field of topological materials. Yeah, it's really an honor to have him here, and I'll go ahead and switch over to Professor Bradlyn. He can see you all on this camera over here, so if you wave, he'll be able to see you. Yeah, here we are. Take it away, Professor Bradlyn. Or please, let's welcome Professor Bradlyn first.
Okay, everybody can hear me okay? Perfect. Okay, so it's a shame I can't be there in person, but it's a pleasure to be here virtually. I am going to tell you today in these 2 lectures a little bit about the connection between linear and nonlinear response and quantum geometry. So this is something that has really come back to the forefront because of recent advances in Moire materials that I think you heard a lot about yesterday and will hear more about throughout the conference. And so my goal here is to help us all develop a solid foundation in the theoretical connection between these 2 seemingly distinct areas. So I very ambitiously titled this Nonlinear Response in Geometry, but in the interest of doing one thing well instead of doing 2 things poorly, the plan for this talk is going to focus mostly on linear response in geometry. So what we're going to do is, in the first lecture, we'll talk about the theoretical setup for response theory and some general properties of linear response. And the 2 linear response functions that are going to be the most important for the connection to geometry are also 2 of the most experimentally relevant, which are the conductivity and the density-density response function. Then in lecture 2, we'll turn more to the precise connection between geometry and response. And we'll do that by looking at 3 things. The first is the Drude weight and the conductivity. The second is the connection between the conductivity and the quantum geometric tensor, which we'll introduce. And the third is the connection between conductivity and density-density response and an information theoretic measure of geometry called the quantum Fisher information. So this is what I want to walk you all through. So we'll get started. Because of the microphone limitations, we talked about it at the beginning of the lecture. It's probably best to save questions for the end, and then that way, if I can't hear you Connor can repeat the questions, tuning into a microphone. Okay, so with that, let's take a look at the experimentally motivated setup for response theory. So generally what we have is we have some quantum system. In condensed matter, this is usually some quantum material, it's some sample. And if it's just sitting alone in isolation, then we know that there's some Hamiltonian, H naught, H naught has energy eigenstates when the system is in isolation. We'll call the energy eigenstates n, and they have eigenenergies, E sub n. And generally what we want to try and do is do something to the system that lets us learn about the properties of the Hamiltonian, the energies, and the eigenstates. The system is in equilibrium. Then the state of this material is described by some density matrix. We'll call it rho naught. And rho naught is the sum over all of our eigenstates, some probability of being in one of the eigenstates, and the projector onto those eigenstates. This is the equilibrium density matrix in the sense that it's time independent. We're not going to have to assume much about the form of the density matrix, but in most cases in real life, these probabilities are determined by the temperature of the system. So usually, the probability of being in some state is proportional to some Boltzmann factor that depends on the energy of the state. Maybe 2 times throughout this lecture, 3 maybe, we'll use this fact, but most of what we're going to do works regardless of what kind of density matrix we have, as long as it's time independent. Okay, so if the system is just sitting alone, happy in isolation, or in equilibrium with some thermal bath, there's not much going on, everything's time independent, and that means that it's hard for us to learn something about this system just sitting in equilibrium. So typically, to learn something about this material, what we want to do is poke it somehow with some probe, and then see what happens by picking up some signal on some detector. So in a transport experiment, we could poke it by applying a voltage or a current or voltage and measuring a current in the detector. In spectroscopic experiments, we can shine light on the system and then measure the momentum or energy transfer from when the light gets absorbed or reflected. And in a susceptibility measurement, we could apply some external magnetic field or electric field and measure a magnetization or polarization. And our general goal is to take what we know about the probe we apply, what we measure at the detector, and use that to infer something about the properties of the system in equilibrium. So as you can tell by my description of an experiment, I'm a theorist. So now what we can do is get into how we can theoretically describe this sort of situation in the abstract. So in our theory setup, we're going to model our probe as a time-dependent perturbation. So instead of our Hamiltonian H naught, we'll now have a Hamiltonian H naught plus we can have multiple different probe fields. I'll index them by I, capital I, with amplitudes f sub I of t, and the probes coupled to some operators b sub I in the system. So for instance, if the probe were light or electric field, these f sub i's would be the different components of the electric field, and b sub I would be the operator that the electric field couples to. For longitudinal electric field, these would be the positions. Or we were applying a magnetic field, f sub I would be the components of the magnetic field, and our operators would be the angular momentum. There's one additional thing that will make our lives easier later on, which is we do want to assume that our system starts in an equilibrium configuration. And that means that if we let time go far enough back in the past, so t goes to minus infinity, the perturbation should turn off, and we should just be left with our starting Hamiltonian. And we'll use a mathematical trick to ensure that. In our time-dependent perturbation, we'll add a factor of e to the eta t, where eta is a small number, and at the end of all of our calculations, we'll just take the limit that eta goes to 0. So this factor, e to the eta t, ensures the perturbation turns off as t goes to minus infinity. There may be more realistic ways we could do this by just saying the perturbation is 0 before some time and then turns on. But because this exponential factor is a nice smooth function, this will make the theoretical analysis a little bit easier. So that's how we're going to model the probe. Now we need to figure out what the system does. And to do that, we can pick some observable A, and look at how the average of A depends on time, or look at how the average of A depends on time, order by order, in the perturbation. So we're going to take this observable. We know that it has some equilibrium average of A naught. And we're going to see in perturbation theory at each order in the perturbation how our probe of the system changes this average. And that's a very abstract view of what we're going to see at this detector. Okay, so from here on out, I need to make the caveat that I'm going to work in units where h bar, c, and e are all equal to 1. Not so much because it's necessary, but because if I don't say this up front, I'm going to start writing formulas, and then halfway through the lecture, I'll stop writing h bars by accident, and everyone will be more confused. Okay. So let's take this average, A of t, and just write down a phenomenological expansion of what it could possibly look like, order by order, in our perturbing fields. Well, at 0th order, we just have the equilibrium average evaluated with our equilibrium density matrix. Okay. At 1st order, we want to see how how A of t can depend linearly on f. So the most general thing we can have is we sum over all of the components of the field, we integrate over all of the possible times that we could look at f at. We have f of t prime, and then we can have some general function, which I'll call chi1. I'll index it by a and I. It can depend on the time that we're evaluating the average of A at. It can depend on the time that we're evaluating F at. And then it can depend on these convergence factors, which, for reasons that will become clear later, helpful to write that dependence like this. This is just this factor here. Okay, we can continue to second order. We get a similar looking expression, but now we'll have two factors of f. And we can go, I'll write the second order one. Now there's an I1 and I2, some convergence factors that we'll write in a funny for now looking way, two time integrals, I1 and T1, T2, a function I'll call chi2. And e to the minus eta, 2t minus T1 minus T2. And we can continue this on to arbitrary order f. The nth order term is going to look something like n factors of f f I sub I of t sub I, product over all of them, put the sum out front so that everything makes sense. That just made everything work. Sum over all these indices, products of all of these f sub i's with some factors of e to the eta t sub I minus t. And then nth order function chi sub n that depends on all of these indices and all of these functions. So these functions, chi n, are known as our response functions. They're the things that quantify how the system responds to the perturbation. Chi n of t, t1, t2, all the way to tn is called an nth order response function. And these are defined perturbatively, meaning that we can use nth order time dependent perturbation theory to come up with expressions for these functions in terms of the eigenstates and energies of our system. Before diving into the explicit formulas for these response functions, though, it's helpful to think about some general properties that all of these response functions have to satisfy, no matter what the system is that we're considering. So the first thing is maybe a little bit obvious, but it's worth saying. So because these chi's are defined with perturbation theory. This means that they only depend on the unperturbed Hamiltonian. And the unperturbed density matrix and the states, etc. And it's worth emphasizing this because this is the whole reason why these functions are interesting. Because we can do an experiment, measure these functions, and learn something about our system in equilibrium. Okay, building on that, we know that in equilibrium, H naught and rho naught are time independent. Meaning that since chi n only depends on properties of the unperturbed system, which has time translation and variant symmetry, if we shift the time argument of all of our perturbations, so instead of applying our perturbation at some time t, we apply it at some time t plus tau. And then instead of measuring at time t, we measure at time t plus tau. Nothing should change because this function doesn't care whether the origin of time is at 0 or the origin of time is at tau. That means that our response functions if we evaluate each of the times at some shifted argument, just equal to the original function. Which means we can repackage the time dependence of this function. It doesn't actually depend on t and t1 and t2 and t3, etc. all independently. It only depends on differences of the time argument. So we can rewrite the time dependence in terms of t minus t1, t minus t2, all the way to t minus tn. Only depends on time differences. Writing things in this way is helpful because then all of these integrals that we have to determine the average of A, they all just become convolutions of our function chi with our perturbation f. In theory, well, this makes some sort of physical sense because it's telling us that, you take the perturbation at some previous time, integrate it with some envelope that's given by a response function, and get the average. And it will make looking at things later as functions of frequency rather than functions of time very nice. Okay, third general property. We know the arrow of time runs in one direction. So our system should respect causality. And I just lost the iPad, so what this means is that the average of A at some time t shouldn't depend on what we decide to do with the perturbation at future times later than t. So average A of t can only depend on f sub I, t sub I less than t. If we combine that with observation 2, that means that should vanish. Because if this argument is negative, it means that we're looking at a time t that's actually earlier than the time at which we're applying the perturbation. So, time vanishes whenever any argument is negative. Okay. One final point is we've introduced all of these indices and auxiliary integration variables. We now have T1, T2 through Tn. We have I1, I2 through In, and so on and so forth. But really, these are all bookkeeping devices that we put there. The system doesn't know the difference between any of these perturbations. In fact, all of these indices, I sub I and T sub I, they're all dummy indices. If we interchange I1 and T1 with I2 and T2, the system shouldn't care. Mathematically, what that means is that since these pairs, I sub I, T sub I, are dummy indices, our functions chi should be invariant or symmetric under the simultaneous exchange of one of the i's with another I and one of the t's with another t. And this is not super important for linear response, but it is something that is important to keep in mind for generalizing some of the things that we're going to do to nonlinear response. Okay, so that is more or less all we can say without sitting down and doing some kind of perturbative calculation. So that means that the natural thing to do next is to see how we can compute one of these response functions. Okay. Our approach is going to be to use perturbation theory. And so to do that, let's write out what average A of t actually is. So we want to take the average of an operator, we take the trace of that operator times our density matrix evaluated at time t. And we know that the density matrix satisfies the Schrodinger equation. Which we can write as rho of t dot equal to minus I commutator of the Hamiltonian with rho. And let's just insert our form of the Hamiltonian. We have H naught, and then we have our perturbation. And we know what the boundary or the initial conditions on our solution rho of t need to be. We know that as t goes to minus infinity, rho of t goes to our equilibrium density matrix rho. So we'll do the standard thing in perturbation theory. We'll write rho of t as rho naught plus rho 1 of t plus rho 2 of t dot dot dot, where each of these rho sub i's depends on f to the ith order. And we can look at how each of these rho sub i's depends on time by looking at the Schrodinger equation and collecting terms of a given order. So in particular, we insert this expansion into our Schrodinger equation. We find that rho sub n dot of t is equal to minus I commutator of h naught with rho sub n. And then we have our perturbation. Because the perturbation is linear in f, the nth order term in the Schrodinger equation here has rho of n minus 1 of t. So we get a nice recurrence relation for rho sub n dot of t, and we can solve this iteratively by using a Dyson series. So if we plug a similar equation in for rho n minus 1 and so on and so forth, what we find is that rho n of t is minus I to the n and then a bunch of nested time integrals where each one goes up to the time of the next. We have a product over all of our perturbing fields. And then, well, when we have one commutator, we plug in another commutator into it, and we do this until we get down to rho naught. We get commutators of b sub I1 of t1 minus t with commutator b sub I2, t2 minus t. Commutators all the way down to bin tn minus t with rho naught. And then we have our e to the eta t sub I. Okay, this is a pretty unwieldy expression, but it is at least formally exact, and we could go through, take this, plug it into the trace with A, and identify all of our response functions. The most famous and useful for our purposes case is n equals 1, which is linear response. And when n equals 1, well, we only have one of these time integrals, we only have one commutator, everything takes a lot less time to write. You may ask yourself, why didn't we just do this in the first place? We have one factor of the perturbation, so I won't even write the I1. We have one convergence factor, then we have commutator, B with rho naught. So if we want to find our linear response function, pi1, we should take trace of A with rho 1 of t. So trace of A with rho 1 of t sum on I1 minus I. Okay, we have an integral here from minus infinity to t, which I can write as an integral of minus infinity to infinity by introducing a step function. So theta of t minus t1, where theta is the step function. It's 1 if its argument's positive, 0 if its argument's negative. And then I have trace A with e sub I t minus t1, commutator with rho naught. And I should say, this time dependence here means time dependence evaluated with respect to h naught. And our convergence vector. Our perturbation. Okay. We can play around with some trace identities and shifting time arguments around with time translation invariance. And we can rewrite this in a form that is most similar to what we had when we defined chi1. We have our integral, et1, and then I'll put some brackets here, minus I theta of t minus t1. If we shuffle around the arguments of the trace, we can get this to be the trace of a commutator times rho 1, or rho naught, which is an unperturbed average of A evaluated at time t, B evaluated at time t1, average evaluated with respect to rho naught, e to the minus eta t minus t1 times fi with t1. And I put brackets here because if we compare this with our phenomenological definition of the linear response function, we see that this thing in brackets is our chi1. So chi1 ai t minus t1 is equal to minus I step function average the commutator of A at t with B at t1, and then this convergence factor. So this is a formula you may have seen before, in a many-body physics class. This is the Kubo formula for linear response functions. And the Kubo formula is nice because it is an exact expression for linear response function. If we happen to know all of the eigenstates of the unperturbed Hamiltonian, we could use those to compute this correlation function and know exactly what the linear response function is. Okay, so the linear response functions are going to be our primary object of study for the next lecture and a half. We know from our definition that the average of A is given by the convolution of chi1 with our perturbation. And now I've taken the liberty of taking eta to 0 outside the integral so that you can forget about this term here. Because this is a convolution, convolutions look very nice when we take the Fourier transform. So instead of working with time, we can work with frequency. And this is usually a nice thing to do because in many cases, we have some way of applying a harmonic potential or harmonic perturbation so that this x of I actually only has one frequency component, or positive and negative frequency component. So we can define average A of omega, integral over time, average A of t, e to the minus I omega t. And this thing is just a product of the Fourier transform of our response function with the Fourier transform of our perturbation. And if we take this response function and Fourier transform it, I1 AI of omega, well, the theta function tells us that we just integrate from 0 to infinity. Put the minus I out front. We have e to the I omega. Then we have minus eta of t. We can write that as plus I eta all times t. And then our correlation function. Where we've used time translation invariance to move this t over to here. So this is really A of t minus t1 and b of 0, evaluated at ground state, or equilibrium state. And it's helpful to define omega plus is omega plus I eta, and we'll put that in here and just write this exponential factor as e to the I omega plus times t. Okay, so far everything has been pretty general perturbation, general observable we looked at the response for. And using this generality, we can say even more about the structure of our response function chi and frequency space. So for the next half hour, maybe a little bit less so that we have time for questions, we'll look at properties and examples of linear response. Okay, if we take this frequency space form of the Kubo formula, it turns out that there's a very specific way that chi depends on omega that is enforced by causality. It's related to the fact that there's a theta function here. Actually, now we'll put the theta function back explicitly, because we can use the fact that this theta function is here to learn something about the frequency dependence of chi and define another function related to chi that will be very important. So because of, well, let's do the following. Let's take the theta function and let's look at this combination that appears here. Theta of t times e to the I omega plus of t. So as a function, this is equal to e to the I omega plus t if t is greater than 0, 0 if t is less than 0. And we can represent this function as an integral in the complex plane. So consider the following, using the residue theorem. Consider the following integral, 1 over 2 pi I, integral over some auxiliary variable alpha, e to the I alpha t over alpha minus omega plus. If I write this in the alpha plane, here's real alpha, here's imaginary part of alpha. There is a pole here when alpha is equal to omega plus I epsilon. So that's sitting somewhere up here in the upper half plane of alpha, or omega plus I eta. And I want to do this integral. So if t is positive, then that means if the imaginary part of alpha is also positive, that this is a decaying exponential. So when t is positive, I can do this integral by making a closed contour at infinity. I enclose this pole at alpha equals omega plus I eta, and the residue theorem tells me that this integral gives me e to the I omega plus times t. If t is negative, then I can't use this contour anymore because the exponential blows up, but I can close the contour down here if t is less than 0. And there's no poles there, so this integral just gives me 0. Now we can use this representation of the theta function, stick it in here for expression for the linear response function, and rearrange terms a little bit. If we do that, we find that our Kubo formula reduces to, and I'll write things follows. I'll take this 1 over 2 pi I factor, and I'll split it up. First, we'll do an integral over alpha. I'll put a 1 over pi here. I have our alpha minus omega plus. We have 1 over 2i. We have a minus I here. That leaves us with a minus a half. And then we get an integral dt e to the I alpha t. And we have our correlation function. And this combination that appears in the numerator here will define as a function chi double prime of alpha. So this is minus a half times just the ordinary Fourier transform of this correlation function. So we can write the Kubo formula, chi double prime of alpha over alpha minus omega plus. And this function chi double prime is known as the spectral density. Okay, well, why did we do this? Well, a couple of reasons that we'll see. The quickest thing that we can look at is if we stare at this expression here, as a function of omega, what this shows, if I write out omega plus as omega minus I plus I eta, this shows that as a function of omega, if we let omega be complex, so have a real and imaginary part, as long as the imaginary part of omega is positive, there's no poles in this integral. All of the singularities occur when the imaginary part of omega is negative. So this shows us, because of causality, this theta function, our Kubo formula, is analytic for real omega greater than 0. Okay, that's nice. From a physics perspective, what does it help us with? Well, from a physics perspective, this spectral density function has several very nice interpretations. The first thing is, I won't write the formula here, it's an exercise that is, well, actually, yeah, I will write the formula here. So this spectral density, the reason why it's called the spectral density is because if we insert a complete set of states, unperturbed energy eigenstates into this commutator, the time dependence here will give us some e to the I times energy difference times time factors. When we do this Fourier transform, what we actually end up with is just a delta function that restricts alpha to be equal to some energy difference. And if you follow out all the algebra, what we get is that the spectral density is a sum over delta functions, difference of probability of being in various states, and then transition matrix elements of A and B between those states. So this function is called the spectral density because it is related to the density of states at some given frequency alpha, weighted by the matrix elements of our perturbation and the observable that we're looking at. We can say even more, if we take this expression here, which I'll put in a box and label it star. We can use what's known as the Flamel-Melch formula for the tells us we have 1 over x minus I eta, like we have here. This is equal to, and the limit as eta goes to 0, well, almost 1 over x, the principal value of 1 over x. So when this sits in an integral, we have the integral, x goes from minus infinity to some infinitesimal, and then at infinitesimal to infinity, we just exclude 0. And then I times pi times a delta function. Now, if we plug that in here, what we find is that our linear response function looks like 1 over pi times the principal value, integral alpha chi double prime, plus I times chi double prime of omega. And it's convenient to define this first term as chi prime. Now, if we go to our Kubo formula, well, actually, now let's specify to a particular case of interest where the observable A that we're looking at is one of these observables B that our perturbation couples to. So for instance, if we are applying an electric field to the system, which we can represent as coupling to the current. Then our B sub i's are current operators, and we'll look at the average current. The two cases that we are going to consider in a moment, density response and current response, fall into this case. Operator A is equal to one of our BJs. In that case, it's not hard to show that chi double prime of ij of omega, just put in our expression here, take the complex conjugate, this is actually equal to chi ji double prime of omega. So viewed as a matrix indexed by our perturbing fields and the thing we're looking at the average of, this is a Hermitian matrix. Because of that, chi prime is also a Hermitian matrix. So this spectral density that we introduced is actually the anti-Hermitian part of our Kubo formula. So it's the anti-Hermitian part of our response function. So not only is it written as some spectral density representation, we can actually extract it experimentally by looking at the imaginary or anti-Hermitian part of the response. And in the interest of time, we'll just say one other general thing about this. So chi double prime we've seen so far is pretty fundamental. It's tells us about the density of energy levels at frequency, or density of transitions at frequency alpha. We can write the entire response function in terms of it, and it's also the anti-Hermitian part of the response function. It also tells us something very physical. Chi double prime tells us about the instantaneous, or tells us about the power that is dissipated by a perturbation. To see this, what we can do is consider the work that we do on our system by applying our perturbation. So for the power that we apply to the system per unit time, we'll call it dW dt, the time derivative of the average energy of the system. So this is equal to two terms, trace of h times the time derivative of the density matrix plus the time derivative of the Hamiltonian times the density matrix. We saw from our Dyson series that the time derivative of the density matrix is the commutator of, well, it's our Schrodinger equation. It involves a commutator of the Hamiltonian with the density matrix, so the trace of this term is actually 0. And we know what the time derivative of the Hamiltonian is, it's just the time derivative of the perturbation. So this is equal to the trace of our perturbation we can substitute in our Kubo formula here. This has two terms. Oh, forgot the time derivative. One term is the time derivative of f times the equilibrium average of b, and then we get time derivative of f, first change to the average of b is given by our linear response function. Okay, this is, again, a convolution. We can, instead of considering the instantaneous power, we can integrate over time to get the total work done. And when we integrate over time from minus infinity to infinity, well, a perturbation turns off at some point in the future. It's zero infinitely in the past. This term doesn't contribute. We have a time derivative here, so in frequency space, we get an extra factor of omega. What we end up with is 1 over 2 pi, integral over omega, I omega, conjugate of fi, pi ij, and then fj of omega. But the power dissipated is real. It's a real number. We have an I here. So this thing better give us something totally imaginary, meaning that only the anti-Hermitian part of the response function contributes here. And what we end up with is minus 1 over 2 pi integral d omega fi star of omega omega times chi double prime fj. So the spectral density is the thing that tells us how much work is being done on the system. Okay, so that's a lot of general theory of linear and mostly linear response. So now what we're going to do is turn to some particular response functions of interest, and we're going to introduce them now, and then in the next lecture, we'll see how the density-density response, and in particular the current response, are related to quantum geometry. So we'll start with density response. So for density response, our perturbation is something that couples to the density at some point r in the sample. And the observable that we're looking at the response of, is also the density potentially at some other points in the sample. So for instance, we shoot X-ray at the system, which more or less just couples to density, and then we look at the charge density that accumulates somewhere else in the system. So from the Kubo formula, we know what this response function is. Our indices now, I is our continuous coordinate r, j is our continuous coordinate r prime. So we can write this as a function of r and r prime. The Kubo formula tells us convergence factor, take the average of density at one point at time t, density at r prime at time t prime. Now, in many cases of interest, the systems that we are going to care about don't just have time translation symmetry, they also have some kind of space translation symmetry, either continuous translation symmetry or for crystals and condensed matter systems, discrete translation symmetry. And the same way we argued that time translation symmetry meant our response functions only a function of time differences, phase translation symmetry tells us, it's discrete translation symmetry, that this function can only depend on r minus r prime modulo some lattice vectors. And if we write this, then just like we went to frequency space for time difference here, we can go to momentum space to look at how the response of one Fourier component of the density depends on a different Fourier component of the perturbation. So for discrete translation symmetry, this means is we look at the average of one Fourier component of the density at frequency omega. We can define a Fourier transformed response function where we have to, if we just have discrete translational symmetry, the response at Fourier component momentum q can depend on momentum q of the perturbation modulo whatever our reciprocal lattice vectors of our system are. Where this Fourier transformed response function has factor of 1 over the volume of the system that comes from our Fourier transform normalization, and then our Kubo formula. Where we commute rho q with rho g minus q. In most cases of interest, we're going to be concerned with really long wavelength perturbations, where long wavelength means the perturbation varies very slowly over the scale of the Bravais lattice of the system, meaning that we're only really going to care about the case where g is 0, but it's helpful to see the general formula as well. Okay. Last thing I want to say is we can also look at the current response to an electromagnetic field, but there's a subtlety there that we haven't encountered before, which is if we want to apply an electromagnetic field to a system, what we can do is we know how to do this by minimal coupling. What happens is the momentum operator everywhere in our Hamiltonian gets replaced by momentum minus the vector potential. But this means that the Hamiltonian generally doesn't just depend linearly on the vector potential. The linear term is the current, but then there's, in general, higher order terms because there can be a quadratic term in the vector potential known as the diamagnetic current, and so on and so forth. If our Hamiltonian is just p squared over 2m, for instance, then this term here is just the number density of particles. So this means that if we look at the average of the current at some time t and some momentum q, it depends, well, there's a response piece that we can get from the Kubo formula. Depends on q and g, a u minus g with t prime. But then we also have another linear contributions of the current, which we define the current is the derivative of the Hamiltonian with respect to the vector potential. So there's going to be a linear response piece where we just look at the change in little j. But then there's going to be a term linear in A that comes from just the unperturbed average of this j mu nu, which is known as the diamagnetic current, or diamagnetic conductivity. A nu q plus g t. And we need to keep both of these pieces around if we want this average j of q that we compute to be a conserved one. It should be, because it's the charge current and charge is conserved. Okay, one further thing is the vector potential is usually not what we care about. The vector potential is gauge dependence. It's, in many cases, a mathematical tool that we use to represent an electric field. What we're usually concerned about is the response of the current to the electric field, not the vector potential. And we know one way that we can represent the electric field, well, is the minus the time derivative of the vector potential, which means the vector potential is minus the time integral of the electric field. Where we use the fact that we know everything turns off at minus infinity to do the time integral this way. We Fourier transform it, means A nu of q and omega is E nu of q and omega divided by I omega plus. So we can put this together with our Kubo formula expression for the response function to define the conductivity. The average j mu q of omega is sum on g response function sigma mu nu q g omega e of q minus g omega, and sigma mu nu, and this is where we will leave it for the morning, is take into account this factor here. We have minus I over V times omega plus average of this diamagnetic term. And then 1 over V omega plus times the Kubo formula piece for R. J nu G minus Q of 0. And so this is the Kubo formula for the conductivity. So like I said, if the kinetic energy is p squared over 2m, this term here just becomes the electron density number over volume over omega plus times delta G0 delta Q0. But in general, it's not that. It's just the second variation of the Hamiltonian with respect to the vector potential. So what we're going to do when we come back in the afternoon is we're going to start with this Kubo formula for the conductivity. We're going to look at what happens in a general quantum system with periodic boundary conditions and see how the conductivity encodes information about the geometry of quantum states. So I'll stop here and happy to take any questions that people have so far.
questions for Barry?
Thank you so much for your talk. I have a question about slide number 7. I have a question. Thank you so much for your talk. I have a question about the slide number 7.
Oh, slide number 7. Okay. That's this one?
Maybe the next one. 8 is here. So here where you define rho naught in the recursive relationship, I was wondering if we can reformulate this one as a Limblad operator, the very right, the last term, to make the calculation easier. Would that be a good approach into these sort of problems?
So, as we've set up the problem here, the time evolution is still unitary. So, I mean, you could formulate it as a super operator, as a Lindblad super operator, but there'd be no dissipators or anything. You can do that, and it does make the bookkeeping of the series simpler in some ways. But yes, this is a thing you could do. There just won't be any dissipation, at least in the setup that we consider.
Any final questions? All right, let's thank Barry one more time. And so now we have a 15-minute coffee break. Have a lecture after that.